All right, hello everyone. We should be on the air now. And if you're online and have any troubles, please let me know. You should be able to reach me by chat on the YouTube stream, and I'll keep another window open here so that I can see what's going on there. So I promised that I would just spend a couple of minutes and mention a couple of the common problems that I saw in marking the exam. So I'm going to start out with that. I'm not going to go over the whole thing in detail just because we don't have time to do it now, but I'll mention a couple of things that maybe would be easier to describe in person, and then I'll invite everyone to send other questions about other things that you got wrong or weren't sure about to our Google group, and I will answer anything that comes up there for everyone. Good evening. Thank you. I can. Okay. So one of the ones that I found was actually caused the most problems were these ones where all you had to do was state a null and alternative hypothesis. And this surprised me because we did a lot of this, and I thought that those are no surprise questions. You just do it exactly the way that we wrote them out in class, and that's all there is to it. But a lot of people got those wrong. I'm going to pull up an example here. Let's see. So here is an example, except that I can't see the multiple things here. What are an appropriate null and alternative hypothesis for the test? And all I actually, this isn't the one that I want to show because I put in a bunch of examples of acceptable and unacceptable answers. So I want to find one of those. Okay, oh yes, the delays in discharge. So all you had to do to get full credit was put something very simple, just like we did in class, that a null hypothesis that the mean, population mean, because it's a mu is equal to 0, and an alternative that it's not equal to 0. If you put that, you got full credits, piece of cake. But this one is a multiple choice one too. So that's not the one that I wanted. It was really the
one of those essay
open, yeah. Let's see. Yeah. Effects of the environment on development in mice. So we have two groups of mice, one in a stimulus-poor environment and one in a stimulus-rich environment. Let's see if I can make this. Can you read that okay? In a stimulus-rich environment. So what is a null and alternative hypothesis? And all you had to do was state for null hypothesis, mu1 equals mu2, alternative hypothesis, mu1 not equal to mu2. And then it's good if you define what your mu is, where mu1 and mu2 are more ideally are the mean numbers of errors made by mice in rich and poor environments. But the thing that really I think there was a lot of confusion about is there's the impression that these hypotheses are about the groups, this one sample, that the mice in this experiment have the same mean. And I saw all sorts of ways that manifests, but did not distinguish that it's clear that this hypothesis is about population means, and it's meant to have a broader meaning outside of these groups of mice. So let's see, what was the example of a good one in words? The null hypothesis is that richness of learning environment does not affect the ability of mice to learn a maze. And the alternative hypothesis is that the richness of learning environment does affect the learning ability of mice. So you'll notice I'm not even referring to these groups of mice here. It's a more general hypothesis about a population, some very large population of mice. So you can see in here I give some examples of acceptable hypotheses that were actual answers that some of you gave, and some of the ones that were either incorrect or vague. So let's see, I'll read a few of these. The null hypothesis is that the mean number of errors in the group of rats in the rich environment is equal to the mean number of errors in the groups that it is in a poor environment. And this is incorrect because it implies that the hypothesis is about this particular group of rats. You don't need to do a hypothesis test to say whether the mean number for this group of rats is the same or not. I mean, they're not, because they're never exactly the same. Does that make sense? So you see how this hypothesis reads very different. The mean number of errors in the group of rats is equal to the mean number of errors in the other group of rats. Compared to this one that I like, the richness of learning environment does not affect the ability of mice to learn a maze. You see how those are different? So let's see another one. H0 equals rich equals poor. That one just doesn't say anything about means, so it's not a correct specification of the null hypothesis. H0 x1 equals x2. That one I consider not correct because we used x to mean sample means, and the hypothesis is not about the sample means. Null hypothesis is that there is no difference in mean maze learning ability between the rich environment x1 and the poor environment group x2. And again, this just is talking about these groups, and it's using x, which we use to mean sample means. There's no difference in the number of errors made between rats who are raised in stimulus-rich environments and those who are raised in stimulus-poor environment. This is almost right. I mean, I could almost give this one full credit, but it's the way it's using the past tense between rats who are raised, it's only talking about the ones that we actually raised. And the whole point of the inference is it's not just about those rats that we raised in the stimulus-rich and stimulus-poor environments. It's about all rats, right? Or all rats from the population from which this particular sample is taken. And just highlighting this because this is really central to your understanding of hypothesis testing. And I do feel that there is way too much consideration of your sample as being kind of all of the data, or as being like a complete representation of the data about, or the population on which we're drawing inference, that it's just about this sample. But you remember our interpretation of the p-value is the probability of us observing this sample if it were drawn from the population and our null hypothesis is true. Yeah?
Quick question. So that means when we write our hypothesis, it has to be a future tense or present tense?
Present tense is fine.
Okay.
You wouldn't usually use future tense. I mean, the easiest way to do it is just to write out the formula, like as we did in class, and define what mu is. And but yeah, the thing that I don't like is when it makes it sound like your null hypothesis is that the mean number of errors of these two groups is the same, because that is all about the sample, and that's not what the null hypothesis is about.
What's the example on the bottom, just where I thought, where it was, yeah, the mu of group 1. I just thought that would mean that that like the mu, so the underlying population mean belonging to group 1, of which group 1 is a part. You know what I mean? So I mean that one to me just strikes me a little bit.
Yeah, this one's a little bit. It's a little bit confusing, I guess. If it were just mu1 and mu2, where mu1 is the mean for rats raised in a stimulus-rich environment, and mu2 is the number of errors for rats raised in a stimulus-2 environment, then it would be fine. I objected to the reference to these groups because it's talking about these two groups of mice. I mean, there's a bit of a disconnect here because mu is supposed to be about a population, but group 1 is our group of 10 rats. So that's why, I don't know, if you just there was a subscript in here, but you can write out mu or put the Greek letter mu, but just mu1, mu2. And here I say mean number of errors made by mice in the rich and poor environments, respectively. I should change this to present, made by mean numbers of errors made by mice in the rich and poor environments. It's not referring to those groups, and so this was an actual one that I gave full credit to. I don't know, are there any more interesting ones here? The difference in the mean number of errors among the group of rats raised in a stimulus-rich environment and the mean number of errors made among the group of rats raised in a stimulus-poor environment. And again, to me, that is just too much about these particular groups and not about the populations from which they were sampled. And I realize I must not have emphasized this enough in class because these confusions were really widespread. And so I didn't deduct too many points for these things. Like, I think on the first one, I gave a lot of these 2 out of 4, and then it was 2 out of 3 and 3 out of 4 on the subsequent questions. But I just wanted to make sure that everyone reviewing their exam knows that, you know, what hypothesis testing is really about and what these hypotheses are really about. It's not about the means in your samples being the same. Are there any other questions about it before I go on to the lecture? I can briefly discuss any other questions. Yes.
Go over question 9.
Question 9. Let's see. Okay, so let's take a look at.
Or no, the previous one.
Question 8.
I mean,
Question 9, question 8?
9.
9. Okay, so this one was for extra credit. Note, you didn't have to do this one. You could get 3 extra points for doing it because it was hard. But yeah, we can take a look. So N. Haynes assesses the health and nutritional status of adults and children in the United States. Blah, blah, blah. The margin of error associated is plus or minus 3 pounds. So it's about the mean body weight in this sample and a margin of error. Assuming the weights are normally distributed, what percent of individuals weighed between 180 and 186 pounds? So this is a bit of a trick question. That's why it was for bonus points. That the margin of error is about, this is our confidence interval around the mean body weight, but it doesn't tell us anything about the variability of individuals. This would be the variabilities of samples under the central limit theorem. So if you want to talk about the percentage of individuals in here, you have to take this 3 pounds. If you divide that by 1.96, you'll get the standard error. So that's going to be somewhere around 1.5 pounds. And then if you multiply that by the square root of n, square root of 712, that'll give you the standard deviation of the individuals. And then you can use that to calculate the proportion of the probability that is between 180 and 186 pounds.
So the answer is,
Let's see, 6%.
oh really? It's impossible to tell.
No, it's not impossible.
You have to just work in reverse.
Yeah, because you're given the margin of error at 95%. From that, you can calculate the standard error, and because you're given the sample size from that, and you're told that it's a normally distributed population, you can calculate the standard deviation of the weights. And you get one of these if you just use the standard error. Well, you get 95% if you use the standard error. But if you convert that to a standard deviation, it goes down to 6%. Does that make sense? It was a tricky one. Not too many people got that one, but.
But you had a question that was just like where it was 95%. There's like a corollary to this question, I think, right?
I think so.
It's like what percentage, if we took 19 out of something like, I don't know, it was basically the right answer was 95%.
Right. I forget which one that was
The
now.
next one.
Yeah, there it is. Question.
Let's see. What is the probability expressed as a percent that the true population, right, mean weight between the men is between 180 and 186? And the answer is 95 because the margin of error is 6 pounds for the 95% confidence interval. Oh, I see a request online for question 31. So this one you knew the answer to, right?
Yeah, that one.
Yeah, this one is standard confidence interval stuff.
I would never have gotten question 9, ever. Like, just because I would never think backwards.
Right. Well, remember that central limit theorem gives you that relationship between standard deviation and standard error. So you can calculate standard error from standard deviation or vice versa, as long as you have the sample size and as long as you have a normally distributed population. Yes?
I have a quick question.
Yeah.
On a different question that's on the same area. I think it's question like maybe 11.
Yeah, let's see.
I just want to, right there. To me, I think the wording is a little bit strange because it's implying the percentage within the 90% confidence interval.
Mm-hmm.
Is that the wrong way to look at it, or?
So what percentage of 95% confidence intervals for the mean will fail to capture that mean?
I think my incorrect understanding of the question is that it's asking within the 90% confidence interval given to us, what is the percentage that it will fail to capture mu? I thought it was 0% because that's the 90% confidence interval.
No, I mean, one of the interpretations, frequentist interpretation of the confidence interval, a 90% confidence interval, is that if you take random samples and from each one of them calculate a 90% confidence interval, then you expect 90% of them to contain the true population mean and the other percent not to.
Okay. I just want clarification to make sure that I'm like definitely not on the wrong track. Okay.
Do you remember the plot that we made of confidence intervals it was a simulation that showed most of them in black, containing with a vertical line containing the true mean. Most of them overlap with that true mean, but I think they were 95% confidence intervals. So 1 out of 20 of them, more or less, fell outside of, did not contain that true mean. and they were colored in red.
Okay. Thank you.
You're welcome. There was a request from online to look at question 31. Let's see. Oh yeah, this one. So, null and alternative hypotheses for a test against the null hypothesis of New Yorkers being evenly divided over whether the program has been a success. So here is the easy way to write it down. H0 row using a Greek letter because it's a population parameter equal to 0.5, and HA is row not equal to 0.5, where row is the proportion of New Yorkers who believe that Vision Zero program is working. An acceptable one in writing, the null hypothesis, the proportion of New Yorkers who believe the Vision Zero program is working, and the proportion who believe it's not working is the same. This one, a lot of people called it PCAP, and I accepted that just because most people did that, but really PCAP is I think in our notation, it's a sample mean. So it's better to write it using row. Remember, so PCAP, the null and alternative hypotheses are about the population, not just the sample. Oh yeah, so I wrote that here, PCAP equal to 0.5. It should be about the population mean, but you still got full points for this.
Why it's not P greater than 0.5 and less than equal to 0.5?
Because let's look at the question again. Calculate the 95%. Oh no, this is the
31.
Next one down. Down, 31.
down 31. Yeah, but I want to see the one where it is
39.
originally. Introduced. These are just about the confidence interval.
That's it. That's the one.
Okay, let's look at it. Oops, sorry. Question, write down the null and alternative hypotheses for a test against the null hypothesis of New Yorkers being evenly divided over whether the program has been a success. I think that's pretty clear that that's a two-sided alternative.
If it is greater than 0.5, then it will be success. If it is less than 0.5, then it is not success.
So you're asking people, do you think that the program has been successful, yes or no? And our null hypothesis is that New Yorkers are evenly divided over whether it has been a success or not. So under that null hypothesis, 50% of New Yorkers say it's been a success. And it doesn't really matter whether the other 50% say, I don't know, or it's been unsuccessful. Well, I guess the evenly divided here implies that there's only two answers, yes or no. But what you're talking about is a null hypothesis that they're either evenly divided or fewer New Yorkers think it's been successful, which isn't what the question asks. And it's very rare that you would have a one-sided alternative hypothesis. And it's certainly not, there's nothing in here to imply that you should use a one-sided alternative. Tony.
Yeah, I think we had some examples where there were elections and stuff like that, where it was one-sided hypothesis. I might be thinking of it, but I might add that even people that were using this as a one-sided hypothesis, most of them didn't put the equality into the null hypothesis. So the minute you don't have the equal sign, whether it's one-sided or two-sided, like equal to or less than, or equal to or greater than, you're wrong. You have to have equality in the null hypothesis.
Yeah. Well, and the wording here would sound very awkward if we were trying to justify a one-sided hypothesis. The wording would have to be something like against the null hypothesis of half or fewer of New Yorkers thinking that the program has been a success.
I think some people might have done that because the data was like n equal, because like 550 out of 1,000 New Yorkers believe that, I forgot what it was, one way or the other.
Yeah.
So so knowing that that's your data,
Right.
you might have adjusted the hypothesis.
But you remember at what stage you write down your alpha and your null and alternative hypotheses?
Right, prior to data
Before
collection.
you collect data.
Okay.
It's definitely not supposed to be based on your sample. It has to be fully justified in advance of doing your study. And I don't think there's any reason here why you could justify a one-sided alternative. I mean, it has the effect of cutting your p-value in half. So, you know, that is kind of the classic abuse of the one-sided alternative, where you have a p-value of 0.08 and you find that by justifying a one-sided alternative, you can turn your p-value into 0.04 and report a significant finding. All right. Let's get started. Gonna have to zip through this a little bit quickly because we have a guest coming in at by about 6:15. Actually, Tony, would you maybe stop by the security and just tell them to let Kinja Hinterland in?
Sure.
Thank you.
What's your name again?
Kinja Hinterland, Kinjia Hinterland.
They basically let anybody in anyway.
So, I don't know, sometimes it depends. Okay, so we're going to get started on power and sample size calculations and analysis of variance today. A couple things that are very commonly used by data analysis: power and sample size when you're planning for an experiment, and analysis of variance in your data analysis. So just to review from your hypothesis testing and power that we've covered before, remember that we have these two ideas: the true state of nature, the thing that we don't know but we want to make inference on, and then a result of our inference test, which tells us whether or not to reject the null hypothesis. And there are two types of errors that we can make there. There's the type 1 error when we reject the null hypothesis even though it was true, and then the type 2 error where we don't reject H0 even though it was false. And in the example of the prisoner, type 1 error is where we convict an innocent person, so we have false evidence that the defendant is guilty. And type 2 error is where we fail to convict a guilty person because we don't have enough evidence. So just like in the courtroom trial, in the absence of evidence, we accept the null hypothesis, and only if there is sufficient evidence we reject the null hypothesis. These factors affect power being 1 minus the type 2 error rate. So this is your probability that if H0 is in fact false, we're going to correctly reject it. So this is, you know, we think that there is a difference. We perform an experiment to observe that difference. If there is truly a difference of the size that we hypothesize, power is the probability that we correctly reject the null hypothesis. You can improve your power by increasing your sample size. If there is less variability in the population, that will also increase your power. Increasing your alpha, your type 1 error rate, increases your power. And if there is a greater true difference in the means of populations that you're looking at, that also increases your power.
So when you increase your power, you lower your chances of making a type 2 error?
Right. So high power means less chance of a type 2 error. And power is just equal to 1 minus the type 2 error probability. So a power of 90% means you have a 10% probability of type 2 error. And we commonly, when we're designing a study, try to plan for 80 or 90% power.
The probability is the probability of making the type 2 error. Is that what probability means here?
That is beta, the probability of type 2 error.
Okay. So that's synonymous with power.
1 minus beta is the power.
Okay, got it.
Yeah, 1 minus the type 2 error probability. And power, it's called power because it has kind of an intuitive meaning. It's your power to detect a true difference if it exists. So something with, you know, a low-powered test, there's probably no point in doing the study. A very high-powered test means that if there is a difference, you have very high power to detect it. Here's an example why we do power and sample size estimation. Suppose that you're planning a clinical trial to measure the effectiveness of a pain reliever in reducing self-reported pain due to migraines. If we had an estimate from previous studies of the natural variability of self-reported pain and some idea based on preliminary results or some pilot data, or just a hypothesis about how large of an improvement we expect the treatment to make, then we can estimate as the biostatistician helping to plan this study, how many patients must be enrolled to detect this difference at a type 1 error rate of whatever we want, say 0.05. So we know how variable the population is, or we have an estimate of it. We have an estimate or an assumption of how big the difference should be between these two groups. We can calculate with a sample size estimation how many people we're going to need to be able to see that difference distinguished from the natural variability of self-reported pain among people who in the general population. So this is very important in planning studies. You don't want to choose too few people and have a very low power and likely waste your money. You also don't want way more people than you want because you also waste your time and money that way. You want to find, if you have good estimates of those factors that affect the power, you want to get an appropriate power for your study, an appropriate sample size, appropriate power. And this differs in a philosophically in an important way from hypothesis testing. In hypothesis testing, we start out with the assumption that the null hypothesis is true and calculate the probability of observing a sample like ours or something more extreme. And you're all comfortable with that now, right? And that was part of why I kind of spent a while on those null and alternative hypotheses to try to drill this home. But in power and sample size estimation, we take the opposite approach, that we assume that the alternative hypothesis is true, and then go ahead and calculate the probability of rejecting the null hypothesis when we go and perform our hypothesis test. So we're looking into the future saying, okay, I think the alternative hypothesis is true. If we're talking about two means, I think that the true difference between the means is this. Then I'm going to go and pretend that we're doing the null the null hypothesis testing under the assumption of there being no difference and see what is the probability that I'm going to correctly reject the null. I have some pictures here to help make that a little more real. So I've drawn out here a normal distribution under the null hypothesis where let's say this is the difference in means. The true difference in means is 0, and our variability of the standard error here. So this is a sampling distribution I'm drawing out here. It's a mean of 0, standard error of 1, and so if we do when we do our null hypothesis testing, we're going to assume the null distribution is true. We're going to calculate a z-score for our sample, and if it lies somewhere out in this rejection region or out in this rejection region, we're going to reject the null hypothesis because our p-value is less than 0.05. And if our alternative distribution were the same, then our probability of actually observing a sample in that region is the same as under the null distribution. So it's still going to be a 2.5% probability under each of these tails. But what happens if we hypothesize that our alternative the distribution under our alternative hypothesis is actually true, and this difference in means is not 0? So we have an alternative hypothesis that the difference in means between our two samples is 1. And if that is true, our probability of getting something out in this rejection region actually becomes quite a bit larger than 2.5%. So I'm calling this the rejection region because when we do our null hypothesis test, we're going to be assuming the alternative hypothesis, and we're going to be rejecting if our test statistic lies out in this rejection region or in this rejection region. But if the alternative hypothesis is actually true and there's a difference in means of 1, we've got this much larger probability of getting a result out in this rejection region. And I didn't draw it on the left just because here the alternative distribution is shifted to the right, so this is going to be a really vanishingly small probability over this rejection region. So I'm just doing it one tail at a time here.
So what changed between the two examples?
So here, any actual alternative hypothesis is false, and there's no true difference in the means of these two samples. Here I'm saying that under our alternative hypothesis, which is true, there is a difference in means of 1. And so the probability of getting something out in this rejection region is something greater than 2.5%, and whatever it is here, I'm going to double it.
So we would mistakenly accept the null hypothesis, or fail to reject the null hypothesis.
If we get a test sample anywhere down in here, we're gonna incorrectly accept the null hypothesis. So this is a badly powered test because there's a pretty big overlap between these distributions. So there's not a very good chance of rejecting the null, even if the alternative distribution is true. But the bigger that difference in means becomes, or the bigger the sample size becomes, so that it makes the standard error smaller, the less overlap there is in these distributions. So here's an example. The difference in means is still 1, but I've increased the sample size so that the probability of getting something in the rejection region under the true null hypothesis is now getting to be something not bad. There's like an 88% chance here that we get a test statistic out in the rejection region. So the key thing is here, as far as all of our null hypothesis testing goes, we assume this null distribution is true. But we're going to reject it if we get a sample somewhere out in here. And if in spite of our assumption that the null distribution is true, in real life the alternative distribution is true, then in this situation we have a good chance of rejecting the null hypothesis.
So rejection region refers to rejecting the null hypothesis.
Right. Right. So here's a case with the larger sample size and also a larger difference in the means, the difference in means of the two. And we're up to 100% power here because there's basically no overlap between these two distributions. We have an almost 100% chance under this alternative distribution of getting a test statistic that lies in the rejection region of our null hypothesis test. Make sense? Here is a so-called all-purpose power formula that you can use in a number of situations, and it is just based on this graphic here, that the critical value of z for your power analysis is just your hypothesized difference in the means between the alternative and the null divided by the standard error of that difference and minus your critical value of z under the null hypothesis. So this is essentially a z-score calculated under the alternative hypothesis. This is your rejection region. That gives you another z-score, which you can then look up in your z-table to calculate the power. And then here's how you can go ahead and actually apply that to several different situations with one sample tests on the means and proportions and two sample tests on means and proportions. Once you all learn R, it'll be much easier because there are built-in functions for doing a lot of different power estimations for all kinds of different situations where you just enter the things that you know and it calculates the thing that you're missing.
So what does the difference actually refer to in the numerator?
That is this difference in the means under your null distribution and your alternative distribution.
And how do you know that?
It is either estimated from pilot data or it's just hypothesized. So in the example of the sleep study, you could just hypothesize to say, it can be based on pilot data, it can be hypothesized, or it can, by hypothesized, I also mean that it can just be based on what you consider to be a meaningful difference. Like, if you decide that a change in, you need at least a change in 1 point on this self-reported pain scale for that to be clinically meaningful. So you could say that I want a 90% power to be able to detect a clinically meaningful difference in self-reported pain of 1 point on this scale.
So you put 1 as the numerator there?
Yeah, in that example, that's right. You would put 1 in the numerator here.
It's like the difference you want.
Or, yeah, it could be that It's the difference that you're going to be able to detect in your study with the calculated power. If the difference is that big, then your power calculation will be correct. If the true difference is even bigger, then you'll have a better power than you thought. If the difference is smaller than that, then you'll have worse power than you thought. The ideal case is where you know a priori that this is a difference that I'm going to consider meaningful, and it can be based on something defensible as to what you know makes a difference. You can't always say that, but you need to come up with something. So the thing about power calculations, though, generally there are 4 things involved in it. There's the power, there's this difference in means, there's the sample size, and then there is a variability, the standard deviation. Sorry, and there is what am I missing here? The alpha level. And generally, this ratio, the ratio of the difference in means to the standard deviation, you can use that also instead of having them separately, and then there are just 4 things, that ratio and the difference in means to the standard deviation. Number 1, your alpha, your beta are 2 and 3, and your sample size is number 4. If you have any 3 of those things, you can calculate 4. So you can also say, okay, our sample size is fixed, and we'll have 10 people in each group. We want an alpha of this. We want an alpha of 0.05, a beta of 10, or a power of 90%. So then you can calculate, okay, what difference in means are we going to be able to identify? Just giving you a couple more formulas you can use here to make it a little easier for you to calculate sample size. This is under the normal assumption under the population. So, sorry, back. Here, this is for calculating the Z, but this just takes it a step further to calculate sample size. Sorry, and this is for a two-group power calculation, the number of the sample size in each of the groups if they're equal sized. The Z beta, it's the power. So for an alpha of 0.05, then this Z is 1.96, and for 80% power, this Z beta is 0.8. So in a lot of cases, both of these you just plug in. You plug in 0.84 plus 1.96. This effect size, that's the difference in means, and this is what I meant, how it's the ratio of the difference in means to the standard deviation that matters.
So is this the same standard error we were dealing with before? Like standard error of how much we think there's a difference?
This is standard deviation here, not standard error.
Right, no, but I mean on like the previous slide, like the overall formula for Z power. That standard error there, the difference in the denominator. So yeah, it looks pretty much the same as the standard error we've been working with previously.
Yeah, so this is just kind of a shortcut for you calculating this Z power by giving you the different formulas for the standard error on the difference. So the only way that these different situations, the 1 and 2 sample means and proportions tests differ is in how you calculate the standard error. difference in means or proportions, it's the same for all of these. Z alpha over 2 is fixed, it's probably 1.96. So for all of them, Z alpha over 2 is the same. Difference in means or difference in proportions is just a direct subtraction, but there are different formulas for calculating the standard error. And after you do this, you get a z-score that you can look up on your table and calculate what your power is. All right.
I have a question about
Yes.
beta, like how beta is being used. So I'm hearing beta refers to the power in this example, then 1 minus beta is also the power.
No, so 1 minus beta is the power. So this z beta, if for a 90% power, this would be z for 0.1.
This,
Okay.
Yeah. So beta is always the type 2 error rate.
the z for alpha divided by 2, when you're subtracting that from the z-score difference over that standard error. So, sorry, this also on the previous slide, just that general power equation. So yes, the z of alpha divided by 2 is what? That's how do you get that? You just take like 0.05 divided by 2.
This is your rejection region.
Right.
This is the z-score that you will consider statistically significant when you're doing your hypothesis test.
Okay.
So yeah, sorry, I'm writing it here as z for the power 1 minus beta here and writing it for beta here. Here it is again with proportions. Same thing, just and this here I write without the difference. This is the hypothesized difference in proportions for the two populations, and the p times 1 minus p being your variability, square root of that being the standard deviation under the normal assumption for the binomial distribution. And I think I actually should not put hats over these, since these are just hypothesized about the population. I'm going to go ahead and do that. And I'm just going to cross those out. All right, and got just a little bit more time here. So just to summarize here, this delta is that difference under the hypothesized alternative hypothesis, that when we're doing the power estimation, we assume that there is a true difference for a one sample test, a true difference in the mean of whatever it is in our population minus the mean of what is assumed under the null hypothesis. And for the two sample test, it is the difference in the means of the two populations. So under the null hypothesis, we're going to assume that this difference is 0. And under our alternative, we're going to assume when we're doing the power analysis that it is equal to delta. And so I was mentioning the the ideal situation is where you consider where delta is something that is clinically meaningful or otherwise worth detecting. There are different ways that you can come up with the delta. That's probably the best way, as opposed to determining it from pilot data or from other studies. And again, given any three of these things, type 1 error rate, power, sample size, and delta, you can calculate the fourth one. This is just here to help you. I went over these on a previous slide before, but these are those same four things that can all increase the power. Any questions on this before I move on to analysis of variance? You'll have some more chance to learn about power during the lab session.
I was going to ask if we could do an example, but if we're going to do that during the lab.
Do you have an example of it in the lab?
You know, I kind of do it a little bit differently. I show the two, I use, when we get to the lab, maybe I'll start to describe what
Yeah.
I might describe the idea of power.
Okay.
But worst comes to worst, if we don't get to it, I'll put a video up.
All right.
And usually what I do is I calculate what value I need to get my 5%, my alpha 5% in my sample, and what that means if I assume another distribution, what that means in terms of the probability that I would fail to reject a null hypothesis.
Yeah.
And I've set up two formulas and set them equal to each other.
So you're using
Yeah,
this,
exactly,
this calculation.
like that way,
Yeah.
I have two formulas
Yeah.
that are looking at the same points. I can set them equal to each other.
Yeah.
And calculate the power and calculate the sample size.
Yeah.
And so on. I think it's a little bit more intuitive. May not be easier to do, but there really isn't an easy way to do it. There is a really abbreviated formula in the REST text.
The easy way to do it is, I mean, with an online calculator like this, or with statistical software that offers a lot more options than those.
But there is an abbreviated version of the formula that you're using in REST that we used to use for the sample size.
Okay.
Make it a little easier.
Abbreviated compared to this.
Yeah.
Yeah. Okay. Okay. Well, we're pretty close to out of time here, so I'll probably just introduce the analysis of variance to you today. So this is a very general hypothesis test, and it's actually, I mean, there are whole books written about analysis of variance because it covers a lot of different experimental and study designs, and it is just in general a way of using the amount of variance in what you're interested in, whether it be like the weights of people for Mann-Haynes or pain reduction, the amount of that variability that is explained by something that you're hypothesizing might explain some of that variability. So it's a very generally useful approach. So we're just going to cover single factor or one-way analysis of variance, which is where there's just one single thing that you think might explain some of the variability in your outcome, and it's a factor, categorical or binary. We'll go over the assumptions necessary behind that, do an actual hypothesis, and I don't think we'll actually have time, but do some interpretation of the output one-way ANOVA table, and talk about post hoc tests to look at if it's a multiple level categorical variable, where the actual difference is, what levels of that categorical variable help explain the differences or the variability in your outcome. So recall the cell phone study. We looked at it both as a paired test and as an unpaired test. And in the unpaired example, we had two independent groups of participants, each taking this driving test. One group was doing it undistracted, and the other one was doing it while using a cell phone. And we estimated or calculated the mean response time for each of these two groups. The first group with the cell phone and the second one being the control. Made a box plot of it here. And then we used a t-test to do a hypothesis test on the null hypothesis that those two means, or the means of the populations from which those two groups were taken from, is 0. But now suppose instead of having just a cell phone group, we actually have two treatment groups, one that is using voice only and the other one that is using voice plus data. That would be an example of a situation where you could use a one-way analysis of variance. It's no longer just two groups, there are three groups in here. Another example, evaluation of training programs, where we want to see if there's a significant difference in learning time in minutes using 3 different training methods. So again, it's not a 1 sample test, it's not a 2 sample test. There are 3 or more different means that we are comparing. So taking a look at that some sample data for the 3 learning methods, we have, so this is a very small study. It's only 3 observations for each of these 3 methods. So in our descriptive statistics, we've got n equals 3 in each of these groups. We've got calculate a mean and a standard deviation for each of those groups. So it kind of looks here like in methods 1 and 2, there's a small difference in mean of 2 in the sample, and there's a bigger difference in method 3. And in fact, there's not a lot of variability in this either. The standard deviation is only 3.6, so it's quite a bit smaller than this difference in means, which makes me think that maybe there is the populations from which these are drawn from, all people learning by method 3 might actually be different from the populations of people learning by methods 1 and 2. Here's a box plot of the data set. So these first 2 groups have not very much difference, and the third one has a pretty big difference from the first 2. And our analysis of variance is going to essentially be a null hypothesis test that these groups do not help describe the variability in learning time in minutes any more than random variability within those groups if the population means are identical. So why not just do t-tests? For one thing, we would have to do 3 of them. So there's a problem of what we call inflation multiple testing, inflation of type 1 error rate. Each one of those t-tests has a 5% type 1 error probability. So the probability of a type 1 error occurring at least once among all 3 of them is going to be higher than 5%. You could correct, there are ways to correct for multiple testing, but even at that, you're going to end up with not as powerful or robust of a test as a single analysis of variance done on this data set. So we do analysis of variance to compare the difference in means between two or more populations while avoiding the problems of multiple testing in multiple t-tests. This is just an estimation of the probability of having at least one type 1 error if the probability in each one is 0.05. So the probability of not making a type 1 error in each of them is 0.95. If you cube that, that's your probability of not making a type 1 error in any of the three, and 1 minus that tells us that there's now a 14% probability of making at least one type 1 error. This is the problem of multiple hypothesis testing without any kind of correction for it. So the basic idea, if in these groups there's a lot of variability within the groups and not much variability between the groups, it's kind of hard to tell whether the groups make a difference. Whereas if the variability within the groups, like in the right, is kind of small compared to between the groups, then it becomes easier to say that the groups are making a difference. Or put this way, in the density plots, like you're used to seeing for a normal distribution, if you have groups where there's a lot of overlap in these probability density distributions, then it's going to be hard to tell the difference in samples drawn from these two populations. But if there is not so much overlap in the probability distributions, then it's going to be easier to see that difference. I think I will continue this in the next class to give you a chance to have a little bit of a break now. And hopefully Kinja is here, Dr. Hunterland is here outside.
When we get to the lab, I'm gonna kind of be introducing that also.
Okay,
So,
okay.
if we get started on them, then we get the
Okay, good. So the main thing I hope you take from it is that you can use analysis of variance to compare the means of three or more groups.
Your number.
Do I have what?
A phone number.
A phone number? I don't think so. Okay. Okay, for the folks who are online, I gave you another link for the next part of class.
And we got.
Sneaking in this classroom.
You remember?
Yes.
All right.